Hello, welcome back to Young Measures. I was asked to give a Colloquium talk about a topic that would be suitable for a broader audience, including graduate students. And I thought that talking about the general idea behind analysis on metric spaces would suit the occasion. So I started by recalling the definition of a metric space, which I won't do here. But it's interesting sometimes to really zoom out and look from far away at what you're doing. Metric spaces are topological spaces because the balls form a basis for it. And just because it's a topological space, you can talk about connectedness, compactness, continuity of functions on them. But now you have metric, you can talk about uniform continuity, uniform limits of sequences of functions, and so on. Also completeness, now you can talk about, which is a very important concept. On the other hand, what you don't have on a metric space is the notion of vectors or directions. So I am against having extremely dense slides, but this was kind of a fun way of doing it. My list was just to emphasize how versatile and how flexible metric spaces are. For example, look at number 2. Any subset of a metric space is again a metric space, which is far from being true for, say, vector spaces. Fractal sets, finite and infinite graphs, everything, a normed vector space, these are all examples of metric spaces. But another favorite of mine, finitely generated groups. Limits of manifolds is another example, which is close to the notion of Alexandrov spaces. And these were necessitated by talking about how you can have a sequence of manifolds and talk about what happens at the limit. The limit may not be a manifold, but it's close to being one. But to begin with, it's at least a metric space. Sub-Riemannian manifolds, Heisenberg group are very much favorites on Young Measures, so we must mention them. And number 14, you can take any metric space, raise the distance to a power between 0 and 1 and get yourself a new one. With no further structure on a metric space, you can talk about Hausdorff measures and Hausdorff dimension, not of the space, but also any subset of the space. You can talk about rectifiable curves, Lipschitz curves into your metric space, although I must warn, the collection could be empty if your space is totally disconnected, for example. And a very important notion on metric spaces is the notion of Lipschitz functions. We often have a big supply of these functions because you can just take a distance to a point, and that will be a Lipschitz function with values in R1. Then you can post-compose with some other Lipschitz functions into R1 or into other Rn or even other metric spaces and get yourself more and more classes of Lipschitz functions. But what about analysis? First of all, what do I mean by analysis? Let's agree that by analysis we mean when you take derivatives and that derivatives contain some information about your function. Given how vast the class of examples I gave you, which wasn't even exhaustive, given such diversity, is there any hope for some unified theory of analysis on metric spaces? And from these, we expect certain things. For instance, we want them to coincide with the classical theories on Rn. If we take our metric space to be Rn, the theory we build should at least be very close to what we already have there. Same goes with manifolds and graphs. Let's say finite graphs, connected graphs. There's different ways of talking about derivatives on those. Even Laplacians and things have been defined on there. So we want a coincidence with that. We want the theory to be non-trivial for some genuinely non-Euclidean spaces. We don't want a theory that is just applies basically to something Euclidean or extremely close to being Euclidean. In words of Sems, we don't want to repackage the Euclidean theory and present it as a new thing. And we want it to interact nicely with geometry. for example, quasi-symmetry maps, how do, say, a space of subalif functions will behave under changing your metric space quasi-symmetrically. Another desirable property would be that we want the theory to be stable under limits. Say, if you have a sequence of metric spaces with Poincare inequality, you want the limit to also have the similar Poincare inequality. Where do sources for developing such a theory come from? There is analysis itself for the study of variational problems, minimization problems, PDEs, Laplacians, nonlinear potential theory, and so on. Here you don't even have to go too far away from Euclidean space. You could have Rn equipped with a new weighted measure, and this has been used in the study of degenerate elliptic PDE since 80s. So there's good motivation for developing a theory in non-Euclidean settings. As I mentioned, geometry is an important source of developing a theory of analysis. This I will get back to in future slides. So let's move on. In geometric group theory, there has been applications of analysis of metric spaces, and number 4 and 5 are actually, I find, quite convincing enough. For me, these are enough reasons to study analysis on metric spaces. It just deepens our understanding of the classicals. Let's say we take Rademacher's theorem in Rn. Every Lipschitz function is differentiable almost everywhere. How Euclidean is this result? Does the fact that Rn are perfectly foliated, they have the product structure, basically Rn is R1 n times multiplied with itself. Does Fubini's theorem, for instance, which appears in its proof of Rademacher's theorem, for instance, does the fact that we have perfect radial symmetries, does the fact that in Euclidean space you can shift things around, or we have rotations, do any of them play a fundamental role in the validity of Rademacher's theorem? Without going into metric spaces, we will never find out because we have no comparison to make. But it turned out, as I will mention again later, in Chigurh's, for example, theory, that Lipschitz functions are differentiable almost everywhere, pretty much like in the Rademacher's theorem, on metric spaces that support the Poincare inequality. And this is amazing. This shows how deeper this theorem is, and it does not really depend on anything Euclidean, even though the proof may not show that to us in the Euclidean setting. A second example is how Hajwas and Koskela proved that you can get an apparently much stronger Sobolev inequality from a Poincare inequality. And again, this shows, if you look at proofs of Sobolev inequality in Euclidean setting, it uses lots of Euclidean structure like polar coordinates, maybe co-area formula, and whatnot. But because the proof uses those structures, does it mean that the result itself is pretty much only Euclidean? And again, it turns out, no, this is true in much bigger generality. So even if afterward you are only again interested in Euclidean setting, such understanding gives us new approaches, new universal approaches. Maybe you can prove Sobolev inequality in Euclidean spaces with a much nicer, more intuitive proof. By the way, this you can read from Kinnunen's great notes on Sobolev spaces, Juha Kinnunen. Okay, some success stories. Heinonen and Koskela, the guys who defined upper gradients and Poincare inequality and its role in the study of quasi-conformal maps, 1997. Chigurh's result about differentiability of Lipschitz functions that I mentioned. Let me mention 4 first. Laxo proved that for every real number bigger than or equal to 1, there exist metric spaces of dimension alpha that have a doubling measure and support the Poincare inequality. which shows that the theory is far away from Euclidean, really. And similarly, SEMS gives examples of metric spaces that have good calculus on them. They have Poincare inequality, for instance, but they are genuinely not Euclidean. There is no by Lipschitz parameterization from Rn. He even proves that there are no quasi-symmetric parameterization from Rn, which shows that there are examples of spaces with Poincare inequality with nice analysis on them that are truly non-Euclidean. Okay, let's now talk about how we do analysis on metric spaces. The first observation is that we do need measures, and this is not actually a trivial thing. And I learned this from, again, reading Sem's work, that measures there's a good need for measures, and they're not as natural as the metric or the distance itself. Like, you can talk about Lipschitz functions and many other things without any measure, as we did in the beginning. There's good, valid reasons for why we bring in measures, and that can be thought about. But anyway, to do zero-order analysis, that means analysis where we do not yet take any derivatives. To do such analysis, we only need a mild condition, and that is the doubling of the measure. Measure of twice the ball cannot be extremely larger than the measure of the original ball. From this alone, we get Vitali covering theorem, and from that we get that the maximal function is bounded, and from that we can prove Lebesgue differentiation theorem, for example. So just from a doubling condition, we do get some nice results. By the way, the spaces equipped with the doubling measure are called homogeneous spaces in literature, and so if you want to find stuff about these, search that word. Now, how about derivatives? The first attempt to develop first-order calculus on a metric space came from Hajwas, and this M1P space is called a Hajwas-Sobolev space. He observed that you can characterize W1P functions in nice domains of Rn. These are functions that are weakly differentiable, and those derivatives belong to LP, the very definition of Sobolev space in any textbook you pick. So your function belongs here if and only if there is an LP function, non-negative, which satisfies this pointwise inequality, except maybe from a null set. And if you look at the second half of this equivalence, there is no derivatives involved in that. There is no weak derivative, there is no pointwise derivative. And that is amazing, because then we can use that second half as the definition of a Sobolev space. The only structure we've used is being an LP, which makes sense because we have a measure on our metric space. We assume this. And then there is the distance. That's all. And functions are real valued, so ux minus uy makes sense. Imagine you're Hajwas, it's 1994. You come up with the observation. Do you publish a paper saying that, hey, you can define M1P? No. So what is the test to see if a theory, if a new proposal for Sobolev spaces on a metric space is a good one? Well, I have listed a few items. We maybe cannot have all of them hold, but we want a good subcollection of them to be true for our theory. Number one, it reduces to classical theory, as we mentioned. Lipschitz functions we want included because they are the most natural ones. We want the space to be a Banach space. This is really why we need Sobolev space in Euclidean setting to begin with. We can ask whether our objects in our space satisfy a Poincare inequality, or even better, Sobolev inequality. We can ask whether the derivatives are local. If your function is constant on an open set, does it follow that its derivative in whatever sense we've defined is zero on that set? And we can talk about finer, more delicate properties of Sobolev functions, like how big the set of discontinuities can be. So these are some properties which may or may not hold for a proposed space, but we want at least a good number of them to hold. So M1P does satisfy quite a bit of these. Another approach to a Sobolev theory uses the notion of upper gradients. Actually, many notions do, except for Haiwash's definition. We just mentioned that we can talk about rectifiable curves in a metric space. A metric space in general may have no non-trivial curves or very few of them. But if they do, we will get some good theory. First of all, a definition, we say a Borel non-negative function is an upper gradient of another function if f changes at the endpoints by no more than integral of g over the curve. I'm not, of course, talking about the definitions, going to give you specific definitions here. That's not my aim here. But upper gradients are highly non-stable under limits and choice of almost everywhere representatives. That's a bit of annoyance when it comes to upper gradient. But we can alleviate this problem by introducing a notion of negligible collection of curves. And that's what Shan-McGillingham did by relaxing the requirement in upper gradient to only require for almost every curve in the sense of modulus, which we have talked about on Young measures. And then once you have that, it becomes more flexible and you can define a space N1P, which becomes a very nice theory under assumption of doubling and Poincare inequality. And the Poincare spaces, Poincare inequality is a condition more about geometry of X rather than about functions, which was amazingly clarified in work of Sims. So it basically proved that from existence of an abundance of rectifiable curves between all locations, you can prove a Poincare inequality, which is pretty close to also being a necessary condition. Okay, so this is our second space, M1P and 1P, the Cheeger space. So what Cheeger does is quite interesting. What he says is that, first of all, let's say if a function is in LP and has an upper gradient that is in LP, we welcome them to our class. But to close it off, to make it a Banach space, we include also the following. If f is such that there is a sequence of fi which have upper gradients gi, and fi converges in LP to f, and that supremum of LP norm of gi is finite, we include f in our space. So I recently talked about this in Young measures. This apparently is quite too less to ask because we assume no convergence about the upper gradients here. But it turns out that when p is bigger than 1, from function analysis magic, we end up proving that we can always find other sequences which do converge also with the derivatives converging, with the upper gradients converging. Anyway, it turns out that N1P actually is equal to H1P. And indeed, for spaces that have Poincare inequality and are doubling, all three spaces become equal. Cheeger introduced the space in particular to prove his famous Rademacher theorem that Lipschitz functions are differentiable on spaces supporting Poincare inequality. Okay, how about if we don't have many curves in a space? How do we build Sobolev functions on them, Sobolev spaces on them? First of all, Haiwash definition did not require any curves, but there are also other ways around the problem. We can realize our space as the boundary of a space that does have a lot of curves. Functions on X that you want to study can be realized as traces of functions on the better connected space Y. And in my opinion, here are some current fashions in study of analysis on metric spaces. Thanks for listening and thanks for subscribing to my channel. I see a lot of people do follow my videos without subscribing.